In today's video, we will continue with our methods of proof section of our Intro to Real Analysis playlist. And today we're going to be covering proof by contradiction. Now, proof by contradiction is another powerful technique in real analysis, and it works by allowing us to demonstrate that a statement that we assume to be false leads to a contradiction. The steps are broken down as such. We take a statement that's given, and then we assume that it is false. And then after that, we use logic to show that the false statement leads to a contradiction, and then we can conclude that because the false statement leads to a contradiction, that the original statement must be true. Proof by contradiction can get difficult with some complex examples. So let's start off with an easy example. So we have a statement that says there is no largest even integer. So we want to prove that there is no largest even integer. Well, let's kind of examine what that means. So if you recall in the previous video where I talk about direct proofs, I use a couple of examples that deal with even integers. And I talk a lot about the definition of an even integer in that video. So if you want to reference that video, you can pause right here and go look at it now. But for now, we're going to continue with this example. Let's talk about the even integers for a moment. If you guys recall, they are essentially our common even whole numbers. There's 2, the lowest even integer. Then there's 4, 6, 8, skip a few. You can go all the way up to like 1,124. Skip even more. You can end up with like 9,999,228. And then it could just keep going forever and ever and ever. If we want to show or prove that there is no largest even integer using proof by contradiction, we have to assume that this statement is false via our steps here. So we want to first assume that this is false, that there is in fact a largest even integer, meaning we don't keep counting these even integers forever. They stop somewhere. We just don't know exactly what that number is. So let's give it a letter. We'll call it n. The first part of our proof is assuming that there is a largest even integer, n. So we begin our proof by saying, let's assume the opposite of the statement and there exists a largest even integer, and we called it n. So first we assumed that this statement here is false, and we did that by saying that there is in fact a largest even integer, n. So we're going to assume that there is a large even integer. Well, if that's the case, let's consider what happens when we add 2 to n. So consider the case n plus 2. Now, what happens when we add 2 to n? Well, that means we get another large even integer. In our assumption, we assumed that n was the largest even integer. That's the number, or that's the integer that's the largest of all the even integers. That means, however, if we add 2 to that large even integer, then we get another large even integer. All that means is that n plus 2, is then larger than the number that we said was the largest. So rephrasing one more time. In our proof by contradiction, first we assumed that our statement was false. that this was not true. We said that there is a largest even integer, n, and that's the largest even integer out of all of the even integers. Then we said, well, what happens if we were to add 2 to that largest even integer? Well, that means we get another large even integer, and it's greater than the previous one. So that is a contradiction, because that means this large even integer is no longer the largest even integer. This one is. So as a result, there is no largest even integer, because you can add 2 to this previous one and get an integer even larger. And then the same is true when you add another plus 2, another plus 2, another plus 2, etc., etc. This contradicts the claim that we had one largest even integer. This contradicts our assumption that n is the largest even integer. So this aligns with step 2 of our proof by contradiction methodology. So now we conclude that the original statement is true. Therefore, our assumption that there is a largest even integer must be false. Thus, there is no largest even integer. And then we always end with a shaded box. I'm going to label this therefore. Okay, so let's move on to our next example. The statement is that root 2 is irrational. We want to prove that that is true, and we're going to do so using proof by contradiction. So following our steps, very similar to example number 1, we're going to assume that the original statement that we're given is false. So we're not going to assume that root 2 is irrational. We're going to assume that root 2 is rational. So you need to be very familiar with rational numbers in order to begin this proof. So if a number is rational, that means it can be written as a fraction. If x is rational, then let's call it z. Let's say if z is rational. If z is rational, then it can be written as a fraction of 2 integers in simplest form. So z could be written as x over y, and x is an integer, and y is an integer. And these integers are coprime. It means that their greatest common divisor is 1. GCD is equal to 1. GCD equal to 1. So for square root of 2, that means square root of 2 can be written as a fraction of 2 integers. We're going to do a and b instead of x and y so that we can keep them separate and not get confused in our proof. But that means essentially for our proof, we're gonna start off by assuming that square root of 2 is rational, so it can be written as a over b, a fraction, where the same rules apply. A and b are both integers and their GCD is 1. So let's look at some examples of rational numbers so that you can kind of understand what it means when we're representing a number as a fraction with the GCD of 1, etc., etc. It can all be very complicated talking in terms of letters, so let's look at some more literal examples. So we know that whole numbers are rational numbers. So let's look at 1, 2, 3, 4, ... 52, etc. So 1 can be written as 1 over 1 as a fraction, 2, 2 over 1, 3, 3 over 1, 4, 4 over 1, 52, 52 over 1. All these rational numbers can be written as fractions, and all of their numerators and denominators are integers. And then if you were to try and simplify any of these fractions, you really couldn't. They're in their simplest form, meaning that you can't divide both of these numbers by anything other than 1. Same thing here, same thing here, same thing for all of these. So let's look at some non-whole numbers. We know that we have some repeated decimal numbers like 0.33 repeated, which is essentially 1 over 3. Then you have 0.5, which is 1/2. And the same rules follow. You have both of the numerator and the denominator being integers, and it's in its simplest form, which means you can't divide both of these numbers by anything to reduce this fraction any further. Another good example of a rational number, you do 0.75, which is 3 over 4. Both of these are integers, but you cannot reduce this fraction anymore, so the GCD is 1. But you get the gist. So essentially, we're stating that the square root of 2 can be written as a fraction. And visually, this is what that looks like. So now we can begin our proof. So we start off our proof by assuming that the statement is false, sticking to our steps of a proof by contradiction, sticking to that. So we're going to assume square root of 2 is rational. Then it can be written as square root of 2 is equal to a over b. And what do we say about a and b? Where a and b are integers and coprime integers, or coprime. So coprime is just a fancy word for saying that their GCD is 1. Can't divide these anything by anything other than 1 to simplify them further. So coprime is what that means. So now we are going to make this equation just a little bit more simple to handle. I don't like square roots. A lot of people don't like square roots. So we're going to get rid of square root by canceling it out. We're going to square both sides. So now we're left with 2 on one side, and then a squared over b squared on the other. And now we're going to try and get rid of this fraction so that we can make this equation a little bit nicer. We're going to get rid of the denominator by multiplying by b squared. There we go. This looks a lot nicer to work with and analyze. Looking at this equation here that we've simplified to, we know that a and b are both integers. Now, this equation here is essentially stating that a squared is an even integer. So if you take a closer look here, this looks exactly like our definition of an even integer. If you recall, let me just go off on the side here. Recall that a number, call it x. X is an even integer if there exists an integer k such that x is equal to 2k. What we have here is a squared is equal to 2b squared. Now, since b is an integer, b squared is an integer. Why? If you recall from my previous video, an integer times an integer is just one integer. Since b is an integer, 2b squared makes a squared an even integer since they're equal to one another. This is just an integer. Remember, definition of an even integer is 2 times an integer, and this is 2 times an integer. So this implies just do this. There we go. This implies that a squared is an even integer. So, since a squared is an even integer, then a must also be even. Therefore, a by itself is also an even integer. So let's rewrite a. So let a, what's the definition of an even integer? 2 times an integer. So we're gonna use that. We're not using k, so we'll just use k. So let a equal 2k since it's an even integer. And then we can substitute that into our equation. We're gonna replace, oops, let's use a different color. We're gonna replace a here with 2k. So this new equation becomes 2b squared equals 2k squared. And now let's do some simplifying. We get 2b squared equals 4k squared. And then we can simplify it further by canceling out the 2 on the left side, and it reduces the 4 on the right. We're now left with b squared equals 2k squared. Now, what does this look like? It looks exactly like what we have for a squared. And what did we conclude? We concluded that a squared is even integer. So we can conclude that b is also even. This implies that b squared is even. Therefore, b is also even. Now we can go back to our assumption that the square root of 2 is equal to a over b. We have two integers, a and b, that are co-prime, meaning their GCD is 1, and they can't be reduced anymore. The fractions can't be reduced anymore. They are in their most simple form. Now, we have just arrived that b is even and a is also even. That means for root 2, we have that a and b, where a is even and b is even. And this contradicts our initial assumption that the square root of 2 equal to a over b have a and b as integers and co-prime. They can't be co-prime if both of them are even, because then they can be reduced. So this contradicts our assumption that a and b are co-prime. Therefore, our assumption must be false and square root of 2 is irrational. Let's revisit what we did here. So we assumed that the square root of 2 was rational. We stated that a and b were integers and co-prime, meaning that root 2 written as a fraction could not be reduced any further. So then we just simplified this equation in terms of a and b by removing the square root, doing a little bit of basic algebra here to get a and b on both sides. And through doing that, we saw that a squared was an even integer, therefore a was an even integer. And then since a was an even integer, we used the definition of an even integer to plug that in and simplify further. Then we saw that just like a squared was an even integer, b squared was also an even integer, and therefore b was also even. So we were able to conclude through some simplification and substitution that both a and b were even, which contradicted our claim that they were coprime, because even integers can be reduced by at least 2, and coprime integers in a fraction can't be reduced at all, like our examples up here. So as a result, this contradicted our claim, and our assumption has to be false. And that means the square root of 2 is indeed irrational, which is what we sought out to prove in the first place. Now, this example was a little bit more complicated than our first example, and I hope I didn't lose you too much, but I would appreciate any feedback that you may have. If you want me to go over some more examples using proof by contradiction in another video, just leave a comment down below and I'll be more than happy to do so.